Welcome you all to the first video on transmission and distribution. We have already completed module number 1 and 4 in the class so far. Now I'll be starting with module number 3 followed by module number 5. Both module 3 and 5 will have derivations and problems. Most of it is mathematical. So coming to module number 3, it is performance of transmission lines. As you can see here, it is module number 3, performance of transmission lines. So to make it convenient for you, I've taken the notes that I've already scanned and sent to you so that you can correlate and understand then and there. So here basically we are having three major topics in this module. One is performance of short transmission line, performance of medium transmission line, and performance of long transmission line. Along with that, there is a topic called as Ferranti effect. So totally you'll be studying four topics in this module. I repeat once again, performance of short transmission line, medium transmission line, long transmission lines, and Ferranti effect. So you'll be having a derivation and Phasor diagram for each, and finally after them you'll be having problems on them. So as far as possible, I'll try to cover the theory content, that is the derivation and Phasor diagram, etc. Then later on we can go to the problems. And I'm planning to split this module 3 into 3 videos so that it will be convenient for you to understand one by one. So first let us go through the introduction. What is short transmission line? What is medium line? What is long line? Then only we can go for performance. So first we should understand that. So coming to short transmission line, whenever the length of the transmission line is less than 80 kilometers, 80, it comes under the category of short transmission line. Whenever the transmission line length happens to be in the range of 80 to 250 kilometers, it is called as medium transmission line. And whenever it is above or greater than 250 kilometers, it is called as long transmission line. So it's very easy. If it is less than 80, it is short line. If it is 80 to 250 range, it is medium line. If it is greater than 250 kilometer length, it is called as long transmission line. Now based on this classification, short line, medium line, and long line, before going for the performance analysis of these three lines, first we should understand whether they are coming under lumped parameter system or distributed parameter system. So let us try to understand what is lumped, what is distributed. So here let us talk about lumped parameter system. So you know the fundamental passive elements are R, L, and C. I've taken a simple circuit which is a series combination of R, L, and C, and you're having a source here. So already lumped and distributed parameter system you would have studied in network theory. So just to remind you, the physical elements are concentrated at a specific or a particular point in space. This is the definition for lumped parameter system. Whenever you're having all the physical elements concentrated at a point in space, it is lumped parameter system. Whenever the physical elements are distributed in space, it is called as distributed parameter system. The best example for lumped parameter system is any circuit containing passive elements. Distributed parameter system, the best example is transmission line. So now let us understand what is lumped, what is distributed, what we mean by concentrated at a point in space and all. See here, if you see this circuit, say source R, L, and C, physically you are able to locate R, locate L, and locate C at a particular point in the circuit. Okay. Of course, we know the magnitude of resistance, we know the how much Henry is the magnitude of inductance, and as well as capacitance, some X farads. But physically you are able to locate them. Here only I have resistor, at this place only I have inductor, at this place only I have capacitor. That is what I mean by concentrated at a particular point in space. Now when it comes to distributed parameter system, the best example is transmission line. Already in detail you have learned about different types of transmission line in first module. So also you know that transmission line contains R, L, and C. It contains a combination of R, L, and C together. But when it comes, let us try to understand the difference between lumped and distributed. Say for example, I'll be giving you say around 10 kilometer length of transmission line. Can you ever say that the first 2 kilometers, can you make this statement, say first 3 kilometers contains resistance, next 3 kilometers contains inductance, and the next 4 kilometers contains capacitance? No, it is not so. R, L and C are equally distributed along the entire length of the line of 10 kilometers. You cannot make the statement saying first few kilometers resistance, next few kilometers inductance, and the last few kilometers capacitance. It is equally, it is distributed along the length of the line. So this is what you mean by distributed parameter system. Though you know the value of R, L and C and the impedance of the transmission line, you know the quantity, but you don't know where exactly is R. You cannot, like in your lumped parameter system, here you are able to say at this point only you have R, at this point only you have L, at this point only you have capacitance. But in transmission line, you cannot say that because it is uniformly distributed along the length of the line. At every point of the transmission line, you are having R, L, C. It is, the combination is present. It is an equivalent representation. So this is the difference between lumped and distributed parameter system. Now why I am talking about lumped and distributed parameter system here is, whenever you deal with short transmission line and medium transmission line, they come under the category of lumped parameter system during mathematical analysis. While long transmission line being lengthy, where the effect of capacitance will be applicable, it will be taken into account. So that comes under distributed parameter system. So remember, short transmission line and medium transmission line can be considered to be lumped parameter system, while distributed parameter system will be taken for long transmission line. So this is the main intention behind understanding lumped and distributed parameter system. Next, before starting the performance analysis, we have to understand some terminologies here. See, this is a resistor. These are the two ends of a resistor, end 1 and end 2. The two ends of any element are called as terminals. This is one terminal, this is another terminal. Now if you go for a combination of resistors in this manner, you'll be getting 4 terminals. This is first terminal, second terminal, third terminal and fourth terminal. Terminal is a point where you can connect any other element to that particular place. Say I want to introduce one more resistor here, it can be connected at this point. So here you have 4 terminals, terminal 1, 2, 3 and 4. 2 terminals put together is called as port. So here you are having one port, here you are having another port. Finally, this resistive network can be represented in this block diagram, in this block. That is, this set of resistors or this resistive network is said to be contained within this network, and these 2 terminals, which is one single port, is called as input port, and these 2 are called as output ports. Why we call this as input port is, we always try to connect the source to this, maybe AC source or DC source. Here you try to connect the load, maybe another resistor or any other kind of load you'll be connecting here. Since you're connecting it to the load, it is called as output port. Here it is called as input port. So see, this is a simple resistive network. But coming to the power system, here also you're having generator in the generating station, you're having the transmission network, and on the other side you're having the consumer. So the entire transmission network, whatever you are having, can be represented by this particular box, and we call it as power system network. And at the input port you'll be connecting the generator, at the output port you'll be connecting the load, which is nothing but the consumer. Now let us go further. So the entire power system, for that matter, can be considered as a 2-port network, a standard 2-port network containing input port, output port, and the transmission network is there in between over here. So, and then here, since A and B together is called input port, it is connected to the generator. This voltage what you are seeing here is called as sending end voltage, and IS is sending end current. and here CD, port CD, which is the output port, will be connected to the load, and so this is called as receiving end voltage across CD, and then receiving end current. Sending end voltage, sending end current, receiving end current, and receiving end voltage. You very well know that you already studied two-port network. For any standard bilateral two-port network, these expressions hold good. Vs is equal to AVR plus BIR, Is is equal to CVR plus DIR, and AD minus BC is equal to 1. This is true for any bilateral two-port network. Same thing we are using it here. So Vs Is is given by, in matrix form, if you write this expression, you have A, B, C, D, VR, IR. Now we'll start with performance analysis of short line, medium line, and long line. So before that, we have to talk about equivalent circuit of a transmission line. You know, it contains resistance, inductance, and then shunt capacitance. So here you can see it is called as Z into delta X. Here it is Y into delta X. This is conductance G, which is the reciprocal of resistance. And then Z basically is the series impedance of the transmission line per unit length, and delta X is the actual length of the transmission line. So impedance per unit length multiplied by the length will give you actual impedance. Similarly, here you are having the admittance. Admittance, you very well know, it is the reciprocal of impedance. Z is equal to 1 by Y. So Y is nothing but admittance of the line or shunt admittance of the line per unit length. Delta X is the actual length. So admittance per unit length into the length will give you the actual admittance. And delta X is basically the section of line of length. See, for analysis purpose, we cannot take a definite, we cannot take the entire transmission line length. Only a part of the transmission line will be considering for analysis purpose. Now comes the first one, performance analysis of short transmission line. See, in the previous session, you have seen the equivalent circuit. In that equivalent circuit, you had a conductance and you had capacitance, and then followed by impedance here. Now, when it comes to short transmission line analysis, first you are supposed to draw the equivalent circuit. For that, since it is coming under lumped parameter system, the charging current here is very less, and hence the capacitance is neglected. And power is transmitted at low or medium voltages in case of short transmission line. So the capacitance is neglected. Of course, G also is neglected. So you are left out only with R and X, which is the inductance, R and L basically. So this is the equivalent circuit. So if you remember, this is our circuit. For a short transmission line, this capacitance is neglected. So G also will not be present. You will be left out only with R and L. So whenever it comes to any performance analysis, short transmission line or medium line or long line, we follow the same. First, we try to draw the equivalent circuit. After the equivalent circuit, we try to write the mathematical expressions, find the ABCD constant, then go for Phasor diagram. So now we have understood how we have got this equivalent circuit. We just have neglected the capacitance. Since the charging current is less, it is neglected, and remaining parameters are being written here. R, JXL, and this is the sending end voltage, sending end current, receiving end current, receiving end voltage, and this is impedance Z. So from this equivalent circuit, we know that Is is equal to IR. Since it is connected in series, Is is same as IR. Then using KVL, I'll be writing the expression for Vs. Vs is equal to VR plus Z into IR. Now, first I'll be writing Vs and Is. The same equations, I'm trying to write it in matrix form. So Vs is equal to VR plus ZIR. Is is equal to 0 VR plus IR, because Is is just equal to IR. These two equations have been written in matrix form. Now if you compare this with the standard expression, that is Vs, Is, Vr, IR, A, B, C, D, you will be getting the ABCD constant. A is equal to 1, D is equal to 1, B, Z, C is 0. So the ABCD constants for a short transmission line are A and D equal to 1, B is Z and C is 0. Next, we'll go with the further calculations. Next part is to draw the phasor diagram and write down the performance equations. These equations, what you're seeing is the performance equation. First, let us talk about the phasor diagram. So for drawing the phasor diagram, again I have redrawn the circuit so that we can see here, and I have represented load here. Load always comes at the output port. So you are having receiving end voltage, receiving end current, sending end current. Specifically I have not written because same current is going to flow, and Vs is sending end voltage. So first I'll take the reference for drawing the phasor diagram. I'll take VR, that is the voltage across the load, as reference. And since majority of the load happens to be inductive in nature, current lags the voltage by some angle, which is phi r. So I'll represent IR to be lagging VR by angle phi r. Okay. Then next I'll have to represent voltage across R and XL. That when added with VR should give me Vs. As per KVL, Vs should be equal to voltage across the transmission line plus voltage across the load. Already we are having VR here. Now we'll have to represent voltage across resistor. You know that since it's a resistor involved here, voltage across the resistor and current will be in phase. So already I'm having current. I'll be representing voltage also here. Voltage is nothing but IR into R. Then when it comes to inductor, current should lag the voltage by 90 degrees ideally. So here voltage is set to lead the current by 90 degrees. So this is our voltage vector. So current, this is the voltage across the inductor. Voltage across the inductor is given by IRXL, which is basically leading this current. It is leading the current by 90 degrees. So this is the voltage across your resistor, and this is the voltage across inductor. And finally, if you take from origin to this point, that gives you the resultant, which is Vs. So this is VR, which is voltage across load, and if you use parallelogram law of addition here, if you add the other vector, you'll be getting Vs. Vs is equal to voltage across the effective transmission, the total voltage across the transmission line plus voltage across the load will give me Vs. That is what is being drawn here. And additionally, for analysis purpose, we have taken few decimal points. We have taken few points here, which is B, this is E, F, D, C, and so on. We have just named them. Now I am trying to use Pythagoras theorem here. So here this is the hypotenuse. I'm trying to use Pythagoras theorem for the triangle OEC. So this is O, this is E, this is C. So you know that in Pythagoras theorem, hypotenuse square is equal to adjacent square plus opposite square. So here Vs square is equal to EC square plus OE square. OE is nothing but OA plus AD plus DE. OA plus AD plus DE the whole square plus EC square. That is what is written here. Now in place of OA, I am writing VR. OA vector is nothing but voltage across the load, which is VR. Then comes AD. See, AD is basically IRR cos phi r. This angle is phi r. This angle basically is phi r. So this is the cos component of that. So IRR cos phi r is nothing but AD. Next, I have to write the expression for DE. DE is same as BF here, or FB is same as DE. FB is basically the sine component of this triangle. If you take this triangle, it is the sine component. So the hypotenuse here is IRXL. So it will be IRXL sine phi r. IRXL into sine phi r the whole square. Next, I am interested in expressing EC square. Coming to EC again, we don't write EC straight away. We try to write it as CF minus EF. So first I'll try to write CF. So CF is nothing but cos component of this particular triangle. So it is IR XL cos phi r minus you are having the EF. EF is same as DB. DB is nothing but the cos component, sorry, DB is nothing but the sine component of this particular triangle, which is IRR sine phi r. This thing is IRR sine phi r when this is the angle phi r. Then we take the square root, we try to simplify this and write this in rectangular form. So this is the so it is written in the form of r plus jx, real component and then imaginary component. And our approximation says that the second part, the imaginary part of the component, is generally neglected. So you are left out with the real part of the component, which is Vs is equal to Vr plus IRR cos phi r plus IRXL sin phi r. Then after getting the expression for Vs, we are interested in calculating the regulation and then efficiency. Regulation is given by sending end voltage minus receiving end voltage by receiving end voltage into 100. So if we just take that, Vr plus IR cos phi r, IRR cos phi r plus IRXL sin phi r, that is nothing but your Vs minus Vr divided by Vr into 100. So Vr gets cancelled, you will be left out with IRR cos phi r plus or minus IRXL sin phi r divided by Vr into 100. Now we have to calculate efficiency. Generally, you know, efficiency is given by output by input. Output power is VRR cos phi r, because your output voltage is VR, output current is receiving end current IR, output power factor is, load power factor is cos phi r. So VR IR cos phi r is the output power. Losses are generally given by I square R losses. And then input is generally given by output plus losses. So VR IR cos phi r plus I square R. Just divide output power by input power. Input is nothing but output plus losses. Divide one by the other, multiplied by 100, you will be getting the efficiency. So ultimately, when it comes to this derivation, to summarize, whenever it comes to analysis of short transmission line, first you will have to take the general transmission line representation, talk about short transmission line, write down the equivalent circuit based on whether it is lumped or distributed, then try to calculate ABCD constants by using KCL and KVL expressions here. Write the expression for sending end voltage, sending end current in terms of receiving end voltage and current, and then try to find the ABCD constants. So first part is writing the equivalent circuit, second part is finding the ABCD constant, and third part is drawing the phasor diagram and getting the expression for sending end voltage. So this part you are writing the equal phasor diagram, you will be getting the expression for Vs, imaginary part will be neglected, and finally you will be dealing with final expression with respect to regulation and efficiency. Again, the same approach will follow for medium line and long line. Let me go through medium line and long line in the next videos.